Good morning, sir. I'm K. Vanilla. My roll number is 259558626. I am from CSC Department of AML. Today, my topic is championship retention probability in chess matches. We can go through that. Introduction to chess and algorithm analysis. Chess is a deterministic zero-sum game with perfect information, making it for the algorithmic modeling. And the championship retention refers to a player's likelihood of defending their title over multiple matches or games. This topic bridges game theory, probability, and algorithm design to predict outcomes in structured competitions. We analyze historical match data and player performance matrices using computational methods. Understanding retention probability helps in tournament design, player training, and AI strategy development. This is the introduction to chess that is a deterministic and zero-sum game that with the perfect information and the topic bridges game theory, probability, and algorithm design to predict the outcomes. And we can analyze the historical match data and the player performance metrics using the computational method. And next, modeling player strength data ELO and beyond. The ELO rating system quantifiers players' skill by updating ratings based on the outcomes against the opponents. Higher rated players are expected to win more often, with win probability derived from rating differences. The extensions like Glico and True Skills incorporate uncertainty and volatility in player performance over time. These models serve as input for simulating match outcomes and estimating retention likelihood. We use rating dynamics as a foundation for probabilistic forecasting in the championship scenario. This is the modeling player strength that the ELO rating system quantifies player skill by updating ratings, and the extensions like Glico and True Skills incorporate uncertainty, and the high rated players are expected to win or more often. And we use the rating dynamics as a foundation for probabilistic forecasting that in the championship scenario. And the probability of winning a single game. That given two players with yellow ratings RA and RB, the expected score for the players that EFA equal to 1 plus RB of RA by 400, that this logistic function transforms rating differences into win probabilities between the 0 and the 1. For example, a 200-point advantage gives approximately a 76% chance of winning a single game, and the draws are common in high-level chess and are modeled using adjusted expected scores or separate draw models. And the accurate single game probabilities are essential for building multi-game match models. This is the probability of winning a single game that the function transform rating differences into the two probabilities from the 0 to 1, and the advantage gives approximately a 76% chance of winning a single game, and the draws are common in high level chess, and the single game probabilities are essential for building the multi-game match models. This is the probability of winning a single game, and from single games to match outcomes. So, the championship matches often consist of multiple games, such as 12 game whiles championship contestants, and we model match outcomes using binomial like distributions, accounting for wins, losses, and draws. Monte Carlo simulations can estimate retention probability by sampling thousands of possible match trajectories. This approach captures variance due to randomness even between evenly matched players. The From single games to the match outcomes, the approach can capture the variance due to randomness, and the player retains the title if they win at least as many as games their opposite component, and the model match outcomes using binomial distributions. And next, Markov chains for match state transitions. We represent a match as a sequence of states, each defined by the current and difference between players. The transitions between states depend only on the current state and game outcome probabilities. This memoryless property makes Markov chains a natural fit for modeling chess match progression. Absorbing states occur when one player reaches the required number of wins to secure the match. And we compute retention probability by solving for absorption likelihoods in the chain. The Markov chains for the match state transitions are that we can represent a match as a sequence of states that each one is defined by the current positions of difference between the players, and the memoryless property makes the Markov chains a natural fit, and the absorbing states occur when one player reaches the required number of wins to secure the match. The transition between states depend only on the current state and the game outcome probabilities. This is the so that we can compute the retention probability by solving for absorption likelihoods in the Markov chains. And next, the dynamic programming approaches to match analysis. We define a DP table where each entry of P of I and J represent the probability of the champion leading by I to J games. And the recurrence relations update probabilities based on win, loss, and draw chances at each step. And the base cases handle terminal states where the match concludes due to a decisive lead or game limit. This method efficiently computes exact retention probabilities without full simulation. And the time complexity is for that match analysis is the order of n to the power of 2 for in games, making it scalable for standard match lengths. That the dynamic programming table, we can define a probability of VFIJ that leads to the champion games, and the base cases handle the terminal states, and the recurrence relations update probabilities based on the win or loss of the game. And this method efficiently computes the exact retention probabilities that win or loss and draw chances at each step, and it can retain the probabilities without full simulation. This is the order of n power of 2 is the complexity of for n games. Next, incorporating physiological and fatigue factors. The top players may experience pressure in title defenses that affecting the performance stress, and fatigue over long matches can reduce accuracy, especially in later games. We model these effects by adjusting game in probabilities based on game number or score pressure. For example, a defending champion might have reduced draw avoidance in must-win situations. These behavioral adjustments refine predictions beyond static rating-based models. This is incorporating psychological and fatigue factors that while playing, the top players can experience the pressure in the title defenses, and the fatigue over long matches can reduce the accuracy, and especially in latter games, they can reduce accuracy fatigue. And for example, a defending champion might have reduced draw avoidance. That these behavioral adjustments refine the predictions beyond static rating based models. This is the incorporating psychological factor. And next, data-driven calibration using historical matches. We collect data from past World Chess Championships and elite tournaments, validate our models, and actual retention rates are compared against model predictions to assess the accuracy, and the discrepancies help identify missing factors such as opening preparation or time control effects. And these are the actual retention rates that are compared to against the model predictions, and the machine learning techniques that can tune model parameters to better fit observed outcomes. And this empirical grounding ensures our algorithms reflect real world competitive dynamics. These are the data-driven calibration using the historical matches that we can collect the data from the past World Chess Championships, and the actual rejection rates are compared against the model predictions. And the machine learning techniques can tune the models. And next, Monte Carlo simulation for complex scenarios, that when analytical solutions are intractable, we use Monte Carlo methods to reduce the retention probability, and each simulation runs a full match, sampling game outcomes from calibrated probability distributions. We repeat simulations thousands of times to avoid a distribution of final match results. And this approach easily incorporates non-stationary factors like changing players from or external events. Results provide confidence intervals and sensitivity analysis for key input parameters. This is the Monte Carlo simulation that when the analytical solutions are intractable, then we use the Monte Carlo methods that for the retention probability, and we repeat simulations thousands of times to build the proper of a distribution of final match, and the results provide confidence intervals and sensitivity. Next, algorithmic efficiency and scalability. Exact DP methods are fast for matches up to 20 to 30 games, and the Monte Carlo simulations scale linearly with the number of trials and are easily parallelized. We prioritize algorithms that balance precision, speed, and interoperability for real-world use. These techniques are applicable beyond chess to any sequential competitive system. This is the algorithm efficiency and scalability. And next case study, that Carlsen versus Karuna 2018 World Championship. The 2018 match ended 6-6 in classical games, with Carlsen winning in the rapid tiebreaks, and our DP model predicted a 62% chance of retention, closely matching the actual outcome. This case validates the model's utility in high-stakes real-world championship analysis. The draw frequency, that 12 consecutive draws, highlighted the need to model drawish tendencies in elite play. And the extensions to other games and AI applications like similar frameworks apply to Go, StarCraft, or sports with sequential decisions making. AI agents like AlphaZero use probabilistic outcome estimation to guide search and strategy. The tournament organizers can use these tools to design fairer, more engaging match formats. The core algorithms exemplify how theoretical CS concepts solve practical competitive problems. These are the extensions to other games and AI applications that similar to frameworks, and the AI agents like AlphaZero can use the probabilistic outcomes, and the retention models inform training regimens, and the core algorithms exemplify how theoretical CS concepts are solved. Summary and the key takeaways are that the championship retention probability combines game theory, probability, and algorithms. The Markov chains and dynamic programming offer exact solutions for structured match progression. And the real-world calibration and behavioral adjustments improve predictive accuracy. These methods are scalable, interpretable, and applicable across domains involving sequential competition. Thank you.